Hello, Algebra 2. So the work we've done in Chapter 3 is all leading up to this with the fundamental theorem of algebra. And we're going to be writing polynomials and finding all of the roots in polynomials. So it's similar to what we've been doing, but now we might see some imaginary numbers again. All right, here we go. This here is a nice table from your book because it's summarizing all of the different ways that we talk about zeros or roots or factors. They show up all the time and they all really mean the exact same thing. So just kind of keep that in mind with that table. Okay, here we're going to write the simplest polynomial function we can with the given zeros or roots, these three right here. So we're going to name our polynomial p of x, and we're going to say that that's going to be x plus 2 is a factor, because I know that minus 2 is a root. If x was minus 2 or negative 2, then this would be equal to 0, times x minus 2, and that's because positive 2 is a root, and then times x minus 4. So there it is written out in factors. The next thing we need to do is multiply this all out so that we know what that full polynomial looks like. After you multiply it all out, this is what we end up with. So that is the polynomial with these zeros. Here's my three factors written out because of these three zeros. And here I just rearranged because I'm going to multiply these two together first. I'll save the fractions until the end just because that will be ickier. Okay, here's the rest of it. After I got to this point, to multiply these two out, I used a table because I think that's a little bit easier to keep everything organized. Multiply everything out. I color-coded my like terms here, combine those. Here I had a mixed number and an improper fraction, and in math, at this point, we will keep things in improper fractions. So I just rewrote it like this, and there you go. This all brings us to our main event for this lesson, the fundamental theorem of algebra. And what this is saying is that for any polynomial, whatever degree that polynomial is, that is how many factors or roots that polynomial is going to have. Now, some roots will be a result of multiplicities, and some roots will be complex numbers. Okay, so in this one, we are going to be finding all of the roots of this polynomial. I know it has a degree 4, so I know that I need to be finding a total of 4 roots to this to completely solve it. When I graph it to get me started, I see that it has a root at -1 and a root at 4. That's when it's crossing the x-axis. And so I know that those are 2 of them, but I need to find the other 2. The other 2 roots might be multiplicities of these, or they might be imaginary numbers. So the graphing got us started. Let's do the rest of it. Okay, I've done synthetic division with the 2 roots that I know. So at this point, if I start factoring, I would have x plus 1, that's for that -1 root, x minus 4, that's for that positive 4 root. And then what I'm left with here after synthetic division, down here would be 9, and then a positive x squared. So this is what I have so far, but I need 4 roots. I'm going to take this piece and just work with this. X squared plus 9 equals 0, because I need to know what does x need to be to make that piece equal 0. I'm going to subtract 9 from both sides. I could use the quadratic formula here, but in this one, this will end up being a little bit quicker. I'll take the square root of both sides. I get x equals plus or minus the square root of -9. Now we know we can't do square roots of negatives, but I can break this up into the square root of 9 times the square root of -1. And I would end up with plus or minus 3i. Remember those complex numbers. So continuing to write this out in fully factored form, I have what I already know with those 2 real roots, and then I would have x plus 3i and x minus 3i. So there I have fully factored that polynomial. This one includes some imaginary numbers, and my 4 roots are going to be these 4 right here. Now I knew that there had to be 4 roots because the degree on this polynomial was 4, and some of those roots are imaginary. When I graph this one, definitely pinch and zoom your graph so that it looks like this one, so you get kind of that full shape of what the polynomial looks like. But we see a root at -5 and a root at 1. Here's what we have so far. These were the two roots that we got from the graph, and then this is what's left after a synthetic division. When you solve this one, you get x to be plus or minus 2i in that part. So fully factored, you have these 4 factors, and you end up with these 4 solutions or roots. And that makes sense because the original degree of this polynomial was 4. Next thing in your book is going to be this complex conjugate root theorem. And basically, if a plus bi, that complex number, is a root, then a minus bi is also going to be a root. And so down here, if a polynomial has 2 plus I as a root, then 2 minus I will also be a root. The other part is this review of the irrational root theorem, which we've seen before. If a complex, or excuse me, a irrational number, a plus b times the square root of c, or anytime you have a square root that is not a nice perfect square, then the conjugate of that, or a minus b times the square root of c, would also be a root. And so down here, if the square root of 3 is a root, then the negative square root of 3 is a root too. Okay, so putting this into practice here with a polynomial with these zeros. First one, if the 2 plus I is a 0, then that means x minus 2 plus I is a root, or is a factor. And if 2 plus I is a factor, so is 2 minus I. So then I have to do x minus 2 minus I as well. Then we have x plus the square root of 3. Whoops, I should make that minus, because if the root is positive square root of 3, then my factor needs to say x minus the square root of 3. But then I also need to put down that x plus the square root of 3 is a factor as well. And then lastly, I'll have x minus 1. That's our real root of 1 right there. Okay, so to multiply out this mess right here, I used a table with each term separated out. And if you notice, your i's end up canceling out essentially. And then this last term with a negative I squared, remember I squared is -1. So I have negative 1, which ends up being a positive 1. And so my terms end up being x squared minus 4x, combining like terms, plus 5. And if I go back over here, multiplying out this part isn't quite so bad. I end up with x squared minus 3. So I'm going to write down x squared minus 4x plus 5 times x squared minus 3, and then I still have this x minus 1 from over here. So I'm going to keep multiplying this part. Again, I'm going to use a table for this part to multiply this trinomial and that binomial. Okay, here I multiplied these two terms together in this table right here. I got this, and then I also have x minus 1 here being multiplied. So I'm going to again use a table to multiply these two things out, and then we will be done. Here's my table multiplying out this craziness here. And when I put everything together, including my like terms, I would end up with x to the 5th minus 5x to the 4th plus 6x to the 3rd plus 10x squared minus 27x plus 15. Whew! There it is, the whole thing. And notice that we have a degree of 5 here, which makes sense because if we go way back to the beginning, we had exactly 5 zeros written out in our factors. We're not going to multiply this one all the way out, but let's just practice writing out our factors based on our zeros. If 2i is a 0, then so is negative 2i. And if 1 plus the square root of 2 is a 0, so is 1 minus the square root of 2. And then we also have 3 over here as a 0. So I'm going to have x minus 2i times x plus 2i times minus 1 plus the square root of 2 times x minus 1 minus the square root of 2 times x minus 3. And there would be the whole thing written out as factors. If we went through and multiplied it all out, then we would have it in standard form.